Hi everyone. The next topic is an extension of the least square method. So the topic is robust regression. So the idea of the robust regression is to reduce the impact of outliers by using a different criteria to estimate parameters. So think about the least square estimate. It minimizes the sum of squared residuals. But if we have some outliers, that outlier affects a lot, the result a lot. The primary reason is that we are using the square of residuals. So square function is easy to minimize mathematically, and it corresponds to a Gaussian MLE. So we have some positive aspects, but if we have some large epsilon, it has a huge impact. For example, if epsilon I is equal to 100, then if it reduces to 99, actually the squared residual gets much smaller. But if epsilon j is equal to 1 and this becomes 0, actually impact on sum of epsilon j square is really small. Only the reduction is 1. Here, the reduction is 10 square minus 99 square. So that is almost 200. So the idea of robust regression is we use more robust function instead of square function. In general, that we use the rho of epsilon. We can use this as M estimation. So basically, we change this function, the square function, to rho of epsilon, where rho is some known fixed function. So a typical example is rho of x is the absolute value of x. So even an error is larger, I mean, the epsilon j is large, the impact of epsilon I is much smaller compared to this least square method. So rho is generally called a loss function. So the idea is that, of course, if outliers are really clear, so you know that one observation is recorded by mistake, then you can, remove one by one by hand. But the idea is to remove the impact of outliers automatically and in a more objective way. Okay, so I said the phi of x is equal to the absolute value of x is one typical example for M estimator. That is a common method for robust regression. But actually the R uses a little different function than this. So R uses this function. Phi of x is equal to a quadratic function for negative a to positive a, and the linear function for absolute value of x is larger than a. So maybe it's better it's more intuitive if we write down the figure. So the function is, okay, so the loss function is quadratic up to some point a. And the same thing for x is between negative a and positive a. And after that, we have just linear function. This is just differentiable and continuous, but here is linear. And the same thing for positive side. So this is linear and quadratic. So the idea is that, okay, so for large x or very small x, we don't want to penalize the residual too much. So we only use the linear function, not quadratic function. But between negative a and positive a, we want to have some smooth function for which we can find minimizer pretty easily. And the quadratic function is generally a convenient function when we look for the minimizer. So that's why we use our quadratic function here and the linear function outside. So this is the so-called Huber loss function, and this is used in the default, the robust regression function, RLM, in our language. So this is a sample code for robust regression in R. At first, we need the library mass. So this is a famous package to include many pretty common functions. And here we use this mass package for RLM function, robust linear model. Okay, and the format is the same as usual LM function, just that we change it into RLM. The RLM function have more options, such as we change the loss function, or we even use the robust regression method. But here the default is M estimator with the Huber loss function. And the summary of the RLM, it's very similar. They're almost the same. So estimate, intercept, and okay, so this model is undercount on percentage for Gore and the percentage of African American. So we have these estimates and these standard error and these t-values. So these are basically almost the same as the linear regression, but these estimates are slightly different. Maybe we can focus on the t-value for percentage for Gore and the percentage for African American. If we compare this with previous usual linear regression result, you can see the percentage of African American is probably the more important factor than percentage for Gore, but actually t-value gets larger. So last time LM function 0.928, but now percentage is 1.2115. So in some sense, the result gets better. The result gets, clearer. That doesn't mean it's good, but actually, if we use the robust method, the situation gets better. And probably that is because, okay, so think about the reason with looking at the figure. So this is the scatter plot for these three variables. Under count is Y, and percentage Gore and percentage African American. These are predictors. And probably these observations are problematic. These are kind of outlier, and it influences the linear regression line more. So if we ignore these points, it's clearer that we have some positive trend. So if we reduce the impact of these outliers, the regression result is clearer. Okay. So the idea of the statistics is that if we have many observations and many observations have the same impact, hopefully all observations have the same impact on the final model, then it's pretty robust. But if only a few observations affects the result, so that is just affected by just a few observations. So it can happen by chance. So in that sense, the robust regression, they maximize the power to deduct the truth from the data set. So this is how robust regression works.